Hello and welcome in this sixth lecture of Introduction to Artificial Intelligence and Machine Learning for Engineers. Today what we are going to talk about is to start talking about linear regression, which is one of the most simple yet very useful algorithm to get started with machine learning. So as a reminder, we started to talk about artificial intelligence, AI, and then we saw that machine learning is a subfield of AI. So machine learning is the art of getting computer to learn how to perform a task without being explicitly programmed on how to perform this task. So by using machine learning, we can teach computers to solve problems, to make some prediction by examples, by just relying on previous data, previous examples. And within machine learning, we saw that there is three different classes of machine learning. There is the supervised machine learning, there is the unsupervised machine learning, and then we talked also about reinforced machine learning. Today what we are going to talk about is the case of supervised machine learning. So in this case, when we are talking about supervised machine learning, we are talking about when we have already a collection of data for which we have both the input and the output. So you have some data that are labeled, for which you have both the input and the output that you want to predict. And in this case, what we want is to find a way to map x to y, to be able to predict the value of y as a function of x, to be able to predict the value of a given output as a function of a certain number of input. So that's a case of supervised machine learning. In this case, the output that we are trying to predict will be a continuous quantity that can continuously change. So in this case, we will be in the case of regression as opposed to classification, where the output can only take a given number of discrete values. So today we are going to talk about the case of linear regression, which is one of the most simple method to try to find a way to map some inputs to some outputs by just assuming that the mapping between input and output is governed by a linear relationship, which in many cases is actually not far from the truth. So let's take an example to illustrate what we want to do. So let's assume that we want to consider the example of a spring. So let's assume that we have a spring like this that is attached to a fixed support. And if no force is applied to this spring, it's going to have a length L. And if you apply a given force to this spring, for example, if you apply a tensile force like this, a tensile force F, then the length of the spring is going to increase. So you will have the length is going to increase. So you will have a new length that becomes larger than the old length, which means that you will have an elongation, which we are going to write delta L in this case, where delta L is the new length minus the old length. So in this case, so let's assume that our goal is to be able to predict for a given elongation what is the force that is needed to achieve this elongation. So in this case, our goal is to predict a given output, which in this case is going to be the force. And we want to be able to predict what is the force that we need to apply to a given spring as a function of something that we can observe, which is the input. And in this case, the input will be the elongation, where the elongation would be positive if the spring becomes longer, and the elongation would actually be negative if the spring becomes shorter. So if you are applying a compressive force on the spring. So in this case, our goal is to find a way to map this feature, delta L, and to find a way to, by using this feature, to predict the output or the observation of this problem, which in this case is the force that needs to be applied to the spring in order to achieve this elongation delta L. So there's two ways you can approach this problem. So there is the traditional approach. The traditional approach is you can use it if you have some knowledge about the mechanism that is governing the relationship between the input and the output. So in this case, this is a case where we could have used the traditional approach because if you know some mechanics, you know that you know what is exactly the relationship between the force that you apply to a spring and its elongation. So in this case, you have some scientific knowledge, some mechanistic knowledge about how to map the elongation to the force. So in this case, the traditional approach, if you wanted to solve this using a computer, what you would use is, so you would have your computer, your goal would be to predict a given output. In this case, our goal is to predict the force that needs to be applied to the spring in order to get the targeted elongation. So that's the output. That's what you want to predict. You would want to predict this as a function of an input, and in this case, the input that we want to use is the elongation delta L. So that's what you would feed to the computer. And the other thing that you would feed to the computer is a program, some explicit instruction on how to convert, on how to map delta L to F, on how to calculate F as a function of delta L. So for example, here, if you know the governing law of a spring, then you know that the force is proportional to the elongation with a proportionality constant that is given by the spring constant. So this relationship means that if you apply a given force, then you will get an elongation that is proportional to the force that you apply, or on the other way, that if you apply a given elongation, then the force that you need to apply is also proportional to this elongation. And the higher is the spring constant, the higher is the force that you need to apply. The higher the spring constant, the stiffer is the spring, so the harder it is to elongate it. So the force is proportional to the elongation, and the proportionality constant is the spring constant. And in this case, in the case of the traditional approach, you need to provide this knowledge. So this is, in this case, this is some knowledge that you are providing to the computer, and in this case, the computer knows exactly how to map the input to the output because it has the right knowledge regarding the relationship between the input and the output. So this is the traditional approach. It works when you have some physical knowledge on the relationship between input and output. But in many cases, we don't have this knowledge. For example, if you're trying to predict the behavior of humans, we don't have any laws of physics that is governing the behavior of humans. And even when we are trying to predict things that should be able to be predictable, for example, like the strength of concrete or the risk of fracture of a given structure. In theory, those are things that are still governed by the laws of physics, something that we can describe as an engineering problem that can be solved. But in many cases, problems are so complex that we don't know how to solve them analytically. So in many cases, we don't have this explicit knowledge that allows us to convert the input into an output. So when we don't have this knowledge, then we can move to the machine learning approach. The machine learning approach does not assume any knowledge. The machine learning approach is just going to rely on data and trying to infer some relationship between the input and the output just by learning by example, just by learning data. So in this case, in the case of this paradigm, the computer will do that for you. And in this case, what you are going to do is you are still going to use the input delta L. That's what you know. That's the input that you are going to use. And in this case, rather than having the computer predict the output, you are going to provide the computer with some example of output value. So you're going to provide the computer with some example of measurements that were conducted on a spring, where you measured the elongation of the spring and you measured the force that you needed to apply to achieve this elongation. So in this case, you need to provide some examples. So this is what you are going to be providing to the computer. And the computer, rather than giving you the output, it will actually give you the program. It will tell you how to go from delta L and to map it to F. So in this case, it's exactly the opposite as the traditional approach. You start with the input and the output. So you start with some examples, and the computer will try to find the relationship between those inputs and this output. And in that sense, it's giving you the program that later on, once you have this program, you can use it in order to go back to a more traditional approach, where for a given input, you can now use this program and predict the output. So in this case, you would be able now to predict the force that needs to be applied to a spring to achieve a target elongation. So one important thing to realize is that in the traditional approach, you start with some knowledge about the governing law of a spring, F equal K delta L. And you, using this knowledge, you make some prediction. In the case of machine learning, that's the other way around. You start with some data, and the machine learning algorithm will give you some knowledge back, or it will give you some information about the relationship within those data. So it's giving you some knowledge, and you, in this case, you don't have to provide some knowledge as an input to the machine learning algorithm. It's going to be an output. It's going to be something that the algorithm is giving you as an outcome, rather than something that it needs as an input to give you an answer. So let's assume that we have some example of data. So we are going to illustrate the case of linear regression by taking this example of data. So here, what this plot is showing you is some example of measurement for a given spring. On the x-axis, you have the elongation, so delta L. This is the elongation that you have applied to a given spring. And what you measure as an output is the force. So the force that needs to be applied to this spring in order to achieve this elongation. So in this case, we're going to use those data to illustrate the different ingredients of linear regression. So the first thing is that in this case, in the case of machine learning and linear regression, we are going to train the machine learning algorithm to find a relationship to map how to go from the input, which is delta L. In this case, this is the input, to the output, which in this case is the force, which is what you're trying to predict. So for this, rather than having some knowledge on the relationship between input and output, what you're going to provide to the machine learning algorithm is some examples, some previous data that is going to be useful for the machine learning algorithm to learn by example on how to map the input to the output. So for this, one parameter that is very important is the number of training example that you have. So what is a training example in this case? It's every time you have a given input. So in this case, it's written delta L, but in general, an input is denoted as X. So that's the input. And you are trying to predict a given output. In general, the output is written as Y. So in this case, every time you have a given x and a given y, so every time you have the elongation and the corresponding force, that's an example of a training example. That's an example of measurement. That's one point that you get for a given elongation. You measure the corresponding force. That's one training example. And you are going to do this several times. You need to provide several examples of several different elongation and the corresponding force. So you're going to do this several times. You will get several training examples. So in order to distinguish the different training examples, we are going to rank them or list them in terms of an ID variable, an index variable, which is going to be I. So we are going to write it like this: xi and yi. This is to say that this is the ith, the training example number I. So the ith training example. And so when to get an example, in the case of supervised machine learning, you need to get both the knowledge of X and the knowledge of Y. You need to get both the data and the label of the data. So you need both of those information. So the knowledge, the combined knowledge of what is Y for a given X, this is what we will call a training example. So then you will need several of those training examples. So here we are going to write M as being the number of training example. So you will need several training examples to be able to hope being able to apply machine learning. As a reminder, so X, this is the input. So this is what we are going to call the features. This is the input of your model. This is what you know. And then you have Y. Y, those are the observations. So the observation, so this is what you are trying to predict. This is the output of the model. And so what you want is to come up with a model that will map X to Y. So in the case of linear regression, which is the algorithm that we are going to talk about today, the types of model that we are going to consider are only linear model. So in this case, in the case of linear regression, what you assume is that the relationship between input and output can be expressed as a linear function. So in this case, it means that you can write the model as follows. So the way you are going to try to describe the relationship between the output and the input, you are going to say that you are going to make an hypothesis H as what you assume the output of the model will be. So H will be the hypothesis of the model, and H, the role of this hypothesis is going to map X. So X is the input, the feature. This is what you know. This is the input of your model, and it's going to convert it into H of H, which is the hypothesis, which is what the model think the value of Y should be as a function of X. And in the case of linear regression, the hypothesis of the model will be expressed in terms of a linear function. So a linear function of the type ax plus b, for example, where you have a slope and an intercept. That's a linear relationship. Here, in the context of machine learning, typically we would write this as theta naught plus theta 1 times x, which is the same as ax plus b, or p mx plus b, or whatever is the notation. You need two variables in this case. Theta 1 is the slope of the model, and theta naught is the intercept. It's the value of the hypothesis, the value of the predicted the predicted output when x is equal to 0. So in the case of a linear model, you have two parameters. So in this case, theta naught and theta 1, those are the parameters of the models. As a reminder, so theta 1 is just going to be the slope. Like the higher theta 1, the higher is the increase of the predicted y value as a function of x, and theta naught is just going to be the value of the hypothesis when x is 0. So when you are at x equals 0, the value of the hypothesis is given by theta naught. So in the case of linear regression, this is the model, the types of model that we use. We assume that y, the observation, can be described as a linear function of the feature, and in this case there is only one feature x, so it can just be it can just be described as a linear function of x with one slope, one intercept, so theta naught plus theta 1 times x. So in this case, this is a very reasonable assumption for various reasons. The first reason is that if you just look at the data with your eyes, then it indeed looks like the relationship between the input and the output can be described as a linear function. So indeed, if you look at the data, it looks like it can reasonably be described by a linear function, which in this case means that it makes sense to use linear regression to assume that the hypothesis of the model is going to be a linear relationship, because that's what the data suggest when you look at them. In this case, the other reason that a linear model is a good choice is because if you know a little bit about springs, then you know that the force that that you apply to a spring is going to be proportional to its elongation. So if it's a proportionality relationship, then it can be described by a linear relationship. So in certain cases, for certain types of problems, you don't know what is the relationship between the input and the output. You don't know if it's going to be a linear relationship, a non-linear relationship, an exponential, a logarithmic, an inverse relationship. But in some other cases, you know. When you know, then it gives you some insight about what types of models should be used. If you don't know, then we are going to see different methods that can guess the type of relationship between input and output. But in every case, it's always useful to start with a simple linear regression model, because many phenomenon, especially in engineering, in many cases, the cause is often related linearly to the consequence. When you observe a natural phenomenon, very often the consequence is going to be a linear response of the cause. The cause and the consequence are very often linearly related to each other. Many laws of physics are just linear relationship. For example, if you take the Newton's law of motion, force equals mass times acceleration. So the force is just a linear function of the acceleration in this case. So in many cases, the laws of physics, not always, but in many cases, the laws of physics are just linear relationship where you just express the fact that you have a cause, and this cause is going to induce a consequence, and in many cases the consequence is just proportional to the cause. So when you are doing a linear regression, so you assume that the relationship between input and output is linear. So here that's the only kind of relationship that linear regression will be able to tell you. But in this case, the goal of linear regression is to find what is the best value of the parameters, in this case theta 1 and theta naught, that gives you the best prediction for y. So you want to find what is the best value of theta naught and theta 1 that gives you the best possible model. And the best possible model is when the hypothesis H is going to be as close as possible to the observation. So in this case, like you have two types of variable in this case. You have the training example, the variable of the training example. So this is x. So as a function of x, so if you move along the x-axis, then your hypothesis will give you a different value. So if you take for one value of x, another value of x, etc., the value of the hypothesis will change as a function of x, and then you have some other variables that are the parameters of the model itself, which are the value of the coefficient theta 1 and theta naught. And those variables are not related to the training data, they are related to the model that you are trying to parameterize. So the values of theta 1 and theta naught, this is what is dictating what this red line is going to look like. For example, if you increase the values of theta 1 is the slope of this line. So if you increase the value of theta 1, then you will get some new models that are like this. It's going to change the value of your hypothesis h of x. And if you now change the values of theta naught, for example, if you decrease theta naught, rather than having your initial model like this, if you decrease theta naught, then everything, the intercept is going to decrease. So your model is going to, the hypothesis h is going to decrease as well. So in this case, the goal is to find what is the best hypothesis, what is the best values of theta 0 and theta 1, theta naught and theta 1, that gives you a model that best describe your data, that gives you the hypothesis H that shows the best agreement with the existing training example. So in this case, the training example x and y, those are fixed value. Those are the values that you have measured. So those one are fixed. The values of x is fixed. You have different example x and different values of y. Those are values that are now fixed. And what you are going to vary is the values of theta naught and theta 1. You're going to vary the value of the parameters of the model, theta 1 and theta naught, so as to get the best agreement between your model, the hypothesis, h of x, and the training data that you have. The training data are fixed, and now it's your model that is going to vary as a function of theta naught and theta 1. So in this case, the goal is to find the most optimal values for the parameters. So for the values of theta naught and theta 1 that will yield the best agreement between the hypothesis of this model and the value of y. So just to illustrate this thing, so here we have 3 times the same plot where you have the values of y, so the force, as a function of the elongation, so as a function of x. And in this case, so let's just take a look at what does it mean. So in this case, the values of x and the values of y, those are fixed. Those are the training example. This cannot change. What can change now is the model that you're trying to learn from the data. So what can change now is the values of theta naught and theta 1, the details of your model. So if, for example, if you start with wrong values for theta naught and theta 1, so if theta naught is if the values that you use for theta naught for your model is too high, then it means that your model will look like this, where the intercept of the model is going to be too high. So this is what happens if theta naught is too high. In the case of if theta naught is okay, but theta 1 is too high, then it means that the slope of the model is going to be too high. So it's going to look like this. Theta 1, this case, is going to be too high. And what your goal is to find what is the optimal values of theta naught and theta 1 that gives you the model that appears to show the best agreement with the training data that you are using to train the model. So this would be for some optimal values of theta naught and theta 1. And in this case, again, the values of x and y, the training examples, those are completely fixed. The only thing that is changing now is just the parameters of the model, theta naught and theta 1. So for this, the point of this is to find, like in this case, how do I find the best values for theta naught and theta 1? How do I find the best values of those parameters that gives me the best agreement between the model that I'm trying to construct and the training data? If you can find the best values for theta naught and theta 1, then it means that you are learning some relationship between the input and the output. And in the future, once you have parameterized this model, then it means that you will be able to use this model in the future for new values of x. For example, if you say that for x equal 10, now you will be able to predict, if you have the model, you will be able to predict what is the corresponding force that you will get for a given elongation. So once you have this model, you will be able to make some predictions. So for this, in order to be able to do this, in order to be able to find the best values of the parameters, the first thing that we need is a way to tell how good the model or how bad the model is. So we need to find a way to describe the goodness of the model, how good the model is, how accurate this model is. And in this case, this is what we are going to call the cost function. The cost function is the quantity that is going to tell us how good or how bad the model is. So we need a cost function that describes how far is the model, how far is this red line as compared to the data. And in this case, what we know is the values of x. So we know the values of x. We know the input of the model. So we know that this we always get it right. What we don't know is how well does our model predict the output. So in this case, for example, if you have for this given values of x, the output that is going to be predicted, this is the real values of the output. This is the true value that the output should be. But in this case, this is what your model is predicting. This is the hypothesis of your model is predicting something that is very far from the real output that it should predict, which means that in this case, how good or how bad the model is can be described by this quantity, which is the vertical distance between your model and the true value of the output. So if we take some other example, for example, in this case, for an elongation of 2, this is what the true value should be, but your model is actually predicting something that is much higher. So in this case, again, this quantity here is the value that tells you the error that your model is making. So in this case, for every point, the distance between your model and the true data is what is telling you how good your model is. The higher is this distance, the higher is the distance between your model and the true data, the worse your model is. If you have a model that has a very low distances like this between the true data and your model, then if the distance is small, then your model is very good. So your goal should be to minimize these distances. So here, one thing that is important is that your model depends on the value of those parameters theta 1 and theta naught. That's what you're trying to that's what is really dictating your model. Your model entirely relies on the values of theta naught and theta 1. So very often, rather than writing this model h of x, we're going to write it h theta of x. This is just to remind ourselves that this model depends on theta, that the output of this model depends on the values of theta, where theta denotes theta naught and theta 1. This is to keep in mind that the outcome, the predicted values of this model, it depends on your choice of the values of the parameters theta naught and theta 1. So what's the best way to define this cost function? So for example, if you take here an example where you have your true data, and for example, if you take a model that is not bad but not quite good either, like if this is your model as a function of h, as a function of x, this is your model h of x, this is the hypothesis of your model. So in this case, if we take this model, so the first idea that we could have is to use the distance, the difference between the model and the true data. But if we just use directly the distance, so if we just use the difference between for each x the true value y versus the predicted value h, then you run the risk that sometimes your model will be higher than the true data, and sometimes the model will be lower than the true data. In some case here your model is higher, in some case it's lower. So if you do this, if you just use the distances, and if you sum those differences here, sometimes here the difference will be positive, in some cases the difference will be negative. So we cannot just directly use the difference between the model and the true values. This would be sometimes positive, sometimes negative. It would not make sense. So one other option that we could say is that we said we could use just the absolute value. We could say I'm going to add some absolute values, so that I'm going to sum all those differences here, and I don't care whether those differences are positive or negative. Every time there is a difference, whether it's a positive or negative difference, I'm going to say that the more this difference is large, the worse my model is. But in practice, it's not a good idea to use the absolute value for a reason that we are going to come back in a few minutes. In practice, rather than using the absolute value, what we use is the square. The square is still the same idea as the absolute value, is that the more the difference between the model and the true value is, the higher this square difference will be. So typically, a typical cost function that we can use is the mean squared error. So the mean squared error, what it does is it calculates the average square difference between your model and the true data. So the mean squared error is typically written as MSE, and calculate the average of the square difference. So what you do is you calculate the square difference between your model. So your model is that for each feature x, which will be it will be the case for each training example. So we're going to write this for each xi, where I is the index that corresponds to each individual training examples. For each training example, you are going to calculate what your model is predicting. So you are going to calculate h of theta. So this is the prediction of your model. It depends on theta, and you apply it to the observation x. You apply it to the feature x, and you're going to calculate the difference between the prediction of your model and the true value of the observation, which is y. So this is the prediction. This is what your model is predicting, and this is the true, or the ground truth value. This is the true observation that you are using to train the model. And you are going to take the square difference between the prediction of your model, the hypothesis, and the true observation. And then you are going to take the average of those square difference. This is the mean square difference. So you have to take the average. So you're going to sum this over all the training examples. So you sum this over all the values of I, where I equal 1, 2, 3, etc. So in this case, we have 11 training examples. So you are going to sum over all the values from I equal 1 to 11. And then to calculate the average, you are going to divide by the total number of training example, which we have called M. In this case, M is equal to 11. That's the number of training example. So this is the mean squared error. It tells you an idea of how good your model is. For example, in this case, the MSE here would be pretty low because the model is never too far from the model. Here in this case, the MSE would be high. It means that the model here is not good. MSE would be high here as well. Same thing here, MSE would be pretty high. So in this case, only this model here is the one that shows a low MSE, a low mean squared error, because this is the only model that appears to match pretty well with the data. So in practice, in many cases, we don't exactly use this specific mean squared error as the cost function. So just for to make things easier, and we are going to see why in a few seconds, the way we are going to define the cost function is almost the same as this mean squared error, but we are just going to add a factor 2. We are going to divide this by a factor 2. So we are going to define the cost function as the quantity j. So the cost function tells you how good your model is. So it tells you how good the parameters theta 1 and theta naught are. So the cost function depends on the values of theta naught and theta 1. So we're going to write it j of theta naught. It tells you the cost function. It tells you how good those parameters theta naught and theta 1 are. And we are going to write this cost function as almost the same as the MSE, but just divided by 2. So we're going to write it as 1 over 2m times the sum of the squared error. So the sum of the difference, the square difference between your prediction applied over all the features I and the true observation, and you are going to take the square difference. So this is the cost function that we are going to use in practice for linear regression. So in the case of linear regression, so we said that in this case the hypothesis is going to be necessarily a linear function written as theta naught plus theta 1x. So in this case, your hypothesis is just a linear function of x, and it depends on the choice of the two parameters, only two parameters, theta naught and theta 1, which means that in the case of linear regression, the cost function so depends on only two parameters, theta naught and theta 1, and you can write it if you want as 1 over 2m, where m is the number of training examples, times the sum over all the training example of, so if we replace the expression of the hypothesis in terms of theta naught and theta 1, we can rewrite this as theta naught plus theta 1 times x. So this is the value of the prediction, this is the value of the hypothesis, h of theta, minus the ground truth values, the true value of the output. So this gives you the expression of the cost function in the case of a linear regression problem. So now your goal is to find the most optimal values for the coefficient theta naught and theta 1. So the goal of linear regression is to minimize the cost function. So you want you want your model to be as good as possible. Your model is going to be perfect if the hypothesis becomes equal to the true outputs. This would be a perfect model. If h of theta is equal to y, then that's going to be a perfect model, which means that you want to minimize the cost function. The lower the cost function, the more the cost function is close to 0, the better your model is. So you want to find the values of the coefficient theta naught and theta 1 that will minimize the value of the cost function. So now your goal is to find what is the specific values of theta naught and theta 1 that minimize the value of the cost function j. So one way that you can do this is to plot the value of the cost function as a function of the value of the parameters theta naught and theta 1. So for example, here on this plot, what you have is on the z-axis, so on the vertical axis, you have the value of the cost function j as a function of theta naught and theta 1. On this axis here, you have the values of theta naught, and on this axis you have the values of theta 1. So every time you change the values of the parameter theta naught and theta 1, you will get a different cost function. It means that the training data do not change, but when you change the parameters of your model will become better or will become worse. So the cost function, the goodness of your model, will change as a function of the values of theta naught and theta 1, the parameters of your model. And the problem here is that you cannot try all the possible values of theta naught and theta 1 because there is an infinite number of possible values, like theta 1 and theta naught. They can have any arbitrary values between plus and minus infinity. So you cannot try all of them in order to find the best values of j. And you cannot just plot this function as well, because to plot the function, then you need also to know the value of the function for every single values of theta naught and theta 1. So in this case, this is a simple problem. In this case, there is only a limited number of data, so it's still possible to plot the values of the cost function as a function of the parameters. But in general, when you start to have more than just one feature, when you have more features, then it becomes impossible to plot the value of the cost function. So in this case, you need to find a way to determine what is the optimal values of theta naught and theta 1 without knowing all the possible values of the cost function for any single values of theta naught and theta 1. So another way to conveniently plot the value of the cost function is, rather than to use a 3D plot like this, you can use a contour map. So the contour map tells you exactly the same information, but just viewed from the top. And in this case, so what this is telling you is that, for example, the optimal values for theta naught is going to be close to 0, and the optimal values for theta 1 is going to be close to 2. So this plot shows you exactly the same thing as the 3D plot. It shows you the value of the cost function, which in this case is denoted by the color, in the same way that here the value of the cost function is denoted by the height. So in this case, this plot shows you in a way that is very often easier to read the value of the cost function as a function of the value of the coefficient theta naught and theta 1. And the more the color is dark blue like this, the lower is j. So you are close to the minimum of the cost function, which means that your model is pretty good. And in this case, the more you go towards the edges, the more the cost function becomes yellow. It means that the cost function becomes very high, which means that your model becomes very, very bad at the when the values of theta naught or theta 1 is very bad. So in this case, we find if we were able to plot this function, and if we were able to know the value of the cost function for every single values of theta naught and theta 1, then we would find that the optimal values for theta naught is close to 0, and the optimal values for theta 1 is close to 2. But again, the problem is that in general, we are not able to do this. We are not able to calculate how good the model is for every single values of theta naught or theta 1. So we need to find an algorithm that can allow us to find for a given model, what is the best possible values of the coefficient that will tell us the best representation of the true data, that will give us the model that shows the best agreement possible with the experimental data that you are using. So one algorithm that is very often used in order to find the best values for the parameters of a given model is the gradient descent algorithm. So gradient descent. This gradient descent algorithm is an algorithm that will allow you to find the best possible value for the parameters of your model. So this is an optimization algorithm. It means that you are trying to optimize a function. In this case, the function is j, it's the cost function, and you are trying to find the position, the minimum position of the function, which is when you're trying to find the minimum or the maximum of a given function, that's an optimization problem. You're trying to minimize or to maximize a given function, to find the position that gives you the minimum value. For example, you're trying to find the condition that gives you the minimum cost for something. In this case, you're trying to find the values of the parameters of the model that would give you the minimum difference, the minimum mean square difference, the minimum difference with the true data, so the minimum of the cost function. So the way this algorithm works is as follows. So first, you will start with an initial choice of parameters. So you will start with an initial choice, an arbitrary choice about some initial values of theta naught and theta 1. So this can be anything. It's either you have some intuition about what is the values of theta naught and theta 1, or you will just make an arbitrary choice. For example, let's assume that we are going to use this choice. So this means that in this case, this is the initial choice of theta 0 that you are choosing, and this is in this case, this is the theta 1, so the initial values of theta 1 that you are choosing. So you're starting at this position here. And what you want to find is, starting from there, how do you find this? So this is your initial position, the initial choice, the initial arbitrary choice, and you want to find the optimal values of theta naught and theta 1. You want to find how do you go from this initial position to the optimal value. So it's very similar to if you are walking in some mountains and you don't know what is the topography, what is the altitude around you, and you want to find where is the minimum altitude around you. You want to find where is the position of the valley around you. So of course, if you were able to look around you, then you would find where is the nearest, where is the lowest point, where is the position of the valley. But the point here is that you cannot look around you because you don't know what is the function, the cost function for other parameters. You don't know what is the value of the cost function for every theta 1 and every theta naught values. If you knew the value of the cost function for every single parameter, then you would know already that theta naught equals 0 and theta 1 equal 2 is the best values, but you don't know. You cannot calculate this function for every single values of theta naught and theta 1. So in this case, so it's like you are walking in the mountain, but you are surrounded by some fog. So you don't know what is the good direction that you should walk in order to find the lowest, the position that gives you the lowest altitude, the position of the valley. So in this case, the idea of the gradient descent algorithm is that you are always going to go downhill. That is to say that you are always to go in the direction that makes you go downhill, which means that you will just follow the downhill direction and just try to always go in the direction that makes you go towards a lower altitude. So in this case, step 1 is that you make an initial choice for the position. Stage 2 is that you are going to move, so you are going to change the value of theta naught and theta 1. So you're going to change the values of theta naught and theta 1, and you are going to change this value by every time you move to a new value by going downhill, downhill. So we are going to see what this means to go downhill, but you are always going in a direction that gives you the lowest altitude, the lowest value of the cost function in this case. And then, so you are going to do this, you are going to repeat this by moving step by step, by always going towards the downhill direction until you find the minimum. And so you need to decide that you're going to stop this algorithm when you have found something that is close to the minimum, when you have found the minimum of the cost function. So you stop this optimization algorithm when the minimum has been found. The minimum of the cost function has been found. So in this case, I'm going to put minimum in quotes because you can never find the true minimum of this function. We'll come back to this, but you can get very close. You can get as close as you want to the minimum, but you can never be exactly at the exact location of the minimum. So you will never be able to find the true minimum, but you can get very close. So you need to stop when you are close enough to the minimum. Like whenever your cost function is so low, then you will define a tolerance, and you will say, okay, at this point, I cannot decrease the cost function anymore. So I'm just going to stop here. I define that this minimum that I found is good enough, and I'm going to stop there. So the main idea of this gradient descent algorithm is that you always go downhill. So you always go towards the direction that will minimize the value of the cost function the most. And the way you can find this direction is to calculate the gradient. The gradient of a function tells you the direction towards which the function increases the most. For example, if you take a given point here, the function is increasing in this direction. So the gradient of the function j is going to be a vector that is pointing in the direction where it increased the most. If you take another point here, the direction in which the cost function j is increasing the most will be pointing downwards. If you take a point here, it's going to be like this. So the gradient is always pointing towards the direction in which the function is increasing the most. That's the property of the gradients. So in this case, so as you can see, the gradient is always orthogonal to the contour of this function. Here, those black lines, they show you the position for which the cost function is a constant. So it means that in this case, the cost function is minimum in the middle when it's dark blue, and then the more this color becomes yellow, the more the cost function is increasing, which means that those lines are some ensemble of values of theta naught and theta 1 for which the cost function has a constant value. Here, for all of those position here, the cost function has exactly the same value. So another way to see this is that if you plot this function in 3 dimension, you have some position, like for example something like this here, where the function has a constant value. So you start by the minimum here, and then if you move in different direction, the cost function has the same value. So those contours here tells you the direction along which the cost function doesn't change. Like the gradient here tells you the direction in which the cost function is increasing the fastest, it's increasing the most. And those gradients, they are always orthogonal to those contours. Like those black lines is the direction where the function is not changing. The function is constant over those contours. So if you go orthogonal to those contours, you find, if you point towards the gradient, you find the direction where the function is increasing the fastest. Or if you go in the other direction like this, then you find the direction towards which the function is decreasing the fastest. And in this case, this is what we want. When we go downhill, we want to find the direction in which the function is decreasing the fastest. We know that this is the direction that we should go. When we start from the initial position, we always want to go downhill, because this is the way that is going to bring us to the minimum of this function. So in the case of the gradient descent algorithm, that's the main idea, is that you always go downhill. You will always change, you will always move, you will always change the values of theta naught and theta 1 by always going downhill. And so the way you can summarize this gradient descent algorithm is that at every step, so you are making different steps, at every step you are going to change the values of theta naught and theta 1. So you're going to find some new values for theta naught and theta 1. And so those new values, they will be equal to the old values. So every time you are making one step, you start at a given position, and then you will make one step to move to a new position. So you start at some old position of theta naught and theta 1, and you are going to make one step to move towards the new position. And in the case of the gradient descent algorithm, the direction of this step is always given by the gradient. So in the case of the gradient descent, you always want to go down. So you don't want to go in the direction of the positive gradient. You always want to go in the direction of the negative gradient. So you will add a displacement vector. So your displacement, your new values for theta, you will go in the direction of minus the gradient. So you will add a gradient, you will add a vector, a displacement vector that is proportional to the minus of the gradient, like the opposite of the gradient of the cost function, which is the arrow that we have been representing here. And in the case of the gradient descent algorithm, what you are going to do, now that you have defined the direction, so you always move towards the negative gradient, you need to define how much are you going to move. In order to define how much you move, you need two things. You need to define the direction. So one thing is to say, I'm always going to go downhill. So for example, if you start from there, you go downhill, it brings you here, then 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 it brings you here. If you start from this location here, going downhill would bring you here, then would bring you here, then would bring you here, then would bring you here. So if you go downhill, you go towards the minimum. But it's one thing to know the direction. You also need to know how much are you moving. For a given direction, maybe you will move a little bit or you will move a lot. So the size of the step in this case is going to be determined by first the value of the gradient, but it's also going to be determined, you're going to multiply this by a coefficient alpha. So this coefficient alpha, we call it the learning rate alpha, and it dictates the size of the step that you are doing. Every time you are changing the value of the parameter theta 1 and theta naught, you can make some big steps or some small steps. And if you have a large learning rate, you are going to make some large steps. If you have a small learning rate, then you are going to make some small steps. So that's an important parameter of the gradient descent. So in this case, what this algorithm means is that you start by some initial position, theta naught, theta 1. You are somewhere in this map. You start by an initial position. You want to decide in which direction do you need to move in order to find the values of the coefficient that will give you a minimum for the cost function. So you decide that you are always going to go in the direction of minus the gradient. So this is your position. You are going to add your displacement to determine the new position. The displacement in this case is in the direction of the negative gradient, so that you can be sure that you're always going in the direction where the function is decreasing the fastest, and you multiply this gradient by the learning rate in order to get the new position. At the next step, this new position will become the old position. You will recalculate the gradient, re-multiply by the learning rate, and then determine the new position, etc. The new position becomes the old one, and you repeat this circle iteratively. Every time you move to a new position, the gradient will change. So the direction will change and the value of the gradient will change. So the next step will change. The displacement that you have to make will change after each new step. So you need to recalculate the gradient. Here again, the minus sign comes from the fact that you are always going in the direction of the negative gradient, so that the function is decreasing. If you had a plus sign here, then you would be going in the direction of the positive gradient, which means that you would be moving towards the maximum position of the function. So here, one good thing about linear regression, and it comes from the way we define the cost function. The way we define the cost function as being the sum of the squared error, because we define it like this, because we define it with some square rather than some absolute difference, then you will always be able to find a minimum. You will always have a cost function that is convex like this with a minimum. You cannot find, in the case of linear regression, you cannot find different minimum position, different values of the parameter that would give you different minimum for the cost function. You can have this problem for other types of machine learning model, but in the case of linear regression, by using this cost function, you have only one possible minimum. You have a fully convex function. So in this case, you know that necessarily if you go downhill, if you start at any position that you start, if you go downhill, you will always find the minimum of this function. And this comes from the way we define this cost function. By defining this cost function as being the mean squared error divided by 2, that's how we can make sure that there is only one minimum. If we had defined the function in terms of the sum of the absolute value, the absolute difference between the model and the true observation, then it would have been possible that there is different values of the parameters that gives you the same value for the cost function. So you would have different model that gives you the same exact cost function, which would have been a problem because if you have different minimum, then you don't know what is the best one that gives you the best possible values for theta naught and theta 1. So let's see how it works in practice. So in the case of linear regression, your hypothesis is always going to be a linear function. So your hypothesis always maps the input x linearly to the output based on a linear model, theta naught plus theta 1 times xi. So which means that your cost function, in this case, the cost function associated with a linear model, can always be written as 1 over 2m times the sum over all the training example of theta naught plus theta 1 times xi. So this is your hypothesis. This is the predicted value of your model minus the true value yi, which is the true value based on the training example, and then you take the square difference. So then in the case of the gradient descent, so what we saw is that what you are going to do is to get at every step to get the new values for theta naught and theta 1 So this is like a vector. This is a position. You are going to, at every step, start from the old values for theta naught and theta 1, and you are going to add minus alpha times the gradient of the cost function. So in the case of linear regression, it's pretty easy to calculate these gradients. So the gradient in this case of the cost function, so the cost function depends on two variables. The cost function depends on theta naught and theta 1. So in this case, the gradient is a vector, where the component of this vector is the derivative of the gradient with respect to the first variable, theta naught, and the second component is the derivative of the cost function j as a function of the second variable, which is theta 1. So in this case, in order to calculate the new values of theta 1, what we need to do is to calculate the derivative. We need to calculate the derivative of the cost function j as a function of theta naught and theta 1. In the case of linear regression, this is pretty easy, and we can do this analytically. So in this case, what we need is to calculate those two terms. We need to calculate the derivative of the cost function j as a function of the first parameters theta naught. So we need to calculate the derivative of this term with respect to theta naught. So in this case, first we have the prefactor 1 over 2m. Then we need to calculate the derivative of a sum. The derivative of a sum is the sum of the derivative. So we can put the sum. And then we need to calculate the derivative of a function, theta naught plus theta 1 x minus y to the square. So the derivative of a function to the square is 2 times the derivative of the function times the function itself. So in this case, we get 2 times the derivative of this function with respect to theta naught. In this case, it's just a linear function, and there is only a factor 1 in front of theta naught. So the derivative with respect to theta naught would be just 1. That's the factor 1 that is in front of theta naught. And then we need to add the function itself, which is theta naught plus theta 1 times xi minus yi, which is the function itself. And here you can see why we introduced a factor 2 in the cost function to begin with, because now when we take the derivative, this factor 2 disappears, which means that now we have a simpler equation for the gradient. So we can now write the gradient again as the derivative of the cost function with respect to theta naught can be written as simply 1 over m times the sum over all the training example of theta naught plus theta 1. So the term theta naught plus theta 1, another way that we can write it to simplify is that this term is just exactly the hypothesis of your model. So we can rewrite it again as the hypothesis of your model in terms of the feature xi minus the true output of your model. So that's a more condensed way to rewrite the gradient once we have calculated the value of the derivative. So we can do that again for the other term of the derivative, which is the derivative of the cost function as a function of the second parameter theta 1. So it's exactly the same thing. So first we have the prefactor 1 over 2m. Derivative of the sum is the sum of the derivative. The derivative of the square is 2 times the derivative of the function. In this case, we are deriving the function with respect to theta 1. So in this case, now we have one term, which is xi, which in this case is showing up when we calculate the derivative of this function with respect to theta 1, and then we need to multiply by the function itself, which is theta naught plus theta 1 xi minus yi. So again, we can rewrite this in a more condensed way. We can say that the derivative of the cost function with respect to theta 1 is equal to, again, the factor 2 disappear, so we have just 1 over m times the sum over the training example of, so this time we have a slightly different solution where it's the sum over all the training example of the product between the value of the feature x times the difference between the hypothesis of your model at x minus the true output of your model. So now you have two expressions here. So you have the value of the gradient with respect to the theta naught and the value of the gradient with respect to theta 1. So now this expression allows you to calculate at each step how the values of theta naught and theta 1 is changing. Now the only thing that you need to say is that at each step you will start with the old values for theta naught and the old values for theta 1. Those values you are going to change them to make a displacement to get the new value for theta naught and the new values for theta 1, and this displacement that you are making is given by the values of these gradients. So you are going, in the case of theta naught, you are going to do minus alpha the learning rate times this expression of the gradient that we just calculated, and in the case of theta 1 minus alpha times the gradient with respect to theta 1 that we just calculated. And by calculating those two terms, so those two equations must be solved simultaneously. You start by an initial position, you add a displacement which is minus alpha times the gradient, where the gradient is given by those two expressions, and this gives you a new position. Then this new position becomes the old position, you recalculate the gradient, you making a new step that gives you the new position, etc., etc. And then you can iterate so that eventually you will find the optimal values for the coefficient theta naught and theta 1. So a few things that you can look when you see those expressions. So first, now we can try to understand better the meaning of the minus sign, because here you see that, for example, if you take this term here, the derivative of the cost function with respect to theta naught, if your model is much larger than the true value of the outputs, if the hypothesis of your model, if what your model is predicting is much higher than the output, then you see that the difference between h and y is going to be positive. Your model is going to be higher than the output, then this gradient is going to be positive. Then if your model is too high, then it means that you need to decrease the value of the intercept. So you will, if the model is too high, the gradient here will be positive, so you will need to take your initial value of the intercept. The gradient here is positive, so you will multiply by minus alpha, so you will decrease the value of the intercept. So this term will be negative, so that your intercept will now decrease and will become smaller. It would be the opposite. If your model was too low, then the hypothesis is too low as compared to the true output of the data. Then if your model is too low, this term would be negative. So this term would be negative. You multiply with a minus sign, so now this term becomes positive. It means that now your intercept is going to increase. If your model is too low, the intercept is going to increase to make your model become closer to the real data. And when do you know that you have achieved a good minimum? It's when your model becomes very close to the true value. So the hypothesis H becomes very close to the values of Y, the true output Y. So when this term becomes very, very small because the model is very close to the output data, then it means that this term becomes very, very small, which means that this term here also become very, very, very small. It means that your new position will be almost the same as the new position. Now you are barely moving, like you are not moving anymore because you are very, very close to the minimum of the cost function. You are very, very close to the optimal values for the parameters theta naught and theta 1. So there are two more things that we need to talk about for the gradient descent. The first thing is, when do we stop? When good is good enough? So for this, you need to choose a criterion. Why? Because so if you look at, for example, if I assume that theta naught is equal to 0, so in this case, I'm only going to represent the value of the cost function j as a function of theta 1. We know that the best value in this case for theta 1 is around 2. So if I plot the cost function as a function of theta 1, is going to look like this. So you will start by an arbitrary values for theta 1, which will not necessarily be the best value. Then the gradient descent algorithm will make you go downhill, so you will start moving, and you always move in the direction that makes you go in the towards the direction that makes you decrease the value of the cost function. But one thing is that once you start getting very close to the cost function, you will keep making some tiny baby steps, some tiny steps, but you will never be able to exactly find the minimum, because the gradient descent algorithm will always tell you to move a little bit too much or a little bit too little. So you will never find exactly the true minimum 2. So you will find 2.1 or 1.9 or 1.99 or maybe 1.99999. So you can get, if you are very patient, you can get very, very close to the true minimum, but you can never find the exact true minimum. Another way to look at this is to look at the value of the cost function as a function of the iteration that you are making in your gradient descent, where this is iteration number 1, iteration number 2, iteration number 3, 4, 5, etc. So as you do this, like the more iteration you do, the more the cost function becomes small, but you can never reach exactly 0, or you can never reach the true minimum of j, even if it's not 0. Like you can always have a chance to find a slightly better minimum, but you cannot just continue this forever. So you need to decide a tolerance of when do you decide that the minimum that you have found is good enough, that you have found a value of j that is small enough and that you don't think it's going to decrease much more than this, which means that the values of theta naught and theta 1 that you have found, you expect that they are good enough. They might not be perfect, but they are good enough, so you're just satisfied and you will stop there. So for this, you need to define a tolerance, and there is different way you can do that. One way, for example, is to look at j. So when j starts to when you are very close to the minimum, you see that j starts to plateau and j does not decrease a lot. So one thing that you can look is the relative decrease in j. So if you take one step of gradient descent, the way you can calculate the relative decrease in j, the relative decrease would be the new values of j minus the old value. This is the difference. This is the variation in j. If you want the relative variation, you can divide by the old j. This tells you the difference in j divided by the old j. So you can take the absolute value of this, and this gives you the relative variation of j. When you take the variation and you divide it by the initial value, it gives you the relative variation, like a percentage. And if you know that if you are close to the minimum, so j is close to the plateau, then it means that this relative decrease is going to be very, very low. So one thing that you can say is that if the relative decrease becomes lower than a given tolerance that you have to decide, then this algorithm will stop. You will stop the gradient descent if the relative decrease becomes lower than a given tolerance. And it's up to you to specify the tolerance that you want. For example, a typical value could be, for example, 10 minus 5, or which is the same as 0.001%. In this case, you say that if after a new step of gradient descent, after I moved downhill, I do a new step and I find that the cost function does not decrease more than 0.001%, then it's you consider that it decreased so little that you're very likely you have found a very good minimum already, so you just stop there. So you can change the value of this tolerance. So if you use a higher tolerance, but like 10 minus 4, 10 minus 3, then you will your optimization will stop faster, because it's going to be easier for the model to reach something that is pretty close to the minimum, where the relative decrease will become lower than this tolerance. But if you make your tolerance smaller, like 10 minus 6, 10 minus 7, 10 minus 8, then you make it more difficult to find this minimum. So the algorithm will take a longer time before it finds this minimum that really is so close to the real minimum that the relative variation becomes like very, very, very small. But if you put a lower tolerance, then it means that it will take longer, but the minimum that you will find will be a closer approximation to the real minimum of your cost function. The last thing we haven't talked about yet is how to choose the learning rate. The learning rate alpha that is used in the gradient descent algorithm. So just as a reminder, this learning rate is that at each step of the gradient descent, every time you start with some old position for theta naught and for delta 1, you are going to add a displacement, and this displacement is equal to minus alpha times the gradient of the cost function, and this gives you the new value for the coefficient theta naught and theta 1. So it means that the higher the learning rate, the more you will move at each step, and the lower the learning rate, the lower will be the displacements. So the question is, how do we find in this case the best value for alpha? So let's take, to illustrate the role of alpha, let's take two examples. So let's take a very small alpha first. So again, so you start with an initial position. So this plot shows you the value of the cost function as a function of theta naught and theta 1. So you make an initial decision for your initial values of those parameters, theta naught and theta 1. And then so the gradient descent algorithm tells you that you always move downhill in the direction of the negative gradient, and then you are going to multiply this gradient by alpha. So it means that if you are choosing a very small alpha, then you are going to make a baby step, a very tiny step here. Then you are going to move to a new position, so you are going to calculate the gradient again, make a small step, and this step is going to be very small because your learning rate alpha is very small. So you are going to continue, and you are going to move. You always move in the direction that gives you the the negative gradient. And so those steps are going to be very, very small. And it's going to be even smaller as you get close to the minimum, because as you get close to the minimum, the gradient becomes smaller and smaller. At the minimum, the gradient would be exactly 0. That when you are at the minimum of the function, its derivative is 0, so its gradient is going to be 0, which means that it's going to take a very long time for you to find the minimum of the cost function. If you plot the value of the cost function as a function of the number of iteration that you have in your gradient descent, so initially you start with pretty wrong values of theta 1 and theta naught, so your cost function is going to be very high, and then you are going to do iteration number 1, 2, 3, etc. So your cost function is going to decrease, but it's going to decrease very, very slowly, which means that it's going to take you a very high number of iteration before you eventually find the minimum. So that's not a very that's not a dangerous way, because you will still find the minimum if you're patient enough, but it really can take a very long time, because you are only making like very tiny steps at each step of the gradient descent. So let's see now what happens if you take a very large value of the learning rate alpha. So let's say that you start from the same initial position. So again, you will move towards the direction of the negative gradient. So the direction will not change. But this time, because you choose a very large alpha, you will make a very large displacement, which means that potentially you will move a lot, and you will move up to this point, for example. Now, once you have this point, you will go towards the direction of the negative gradient, which now is in this direction. Again, you will make a very large step because your alpha is very large. Again, now you will go towards the negative gradient, which will go like this, etc. So here, when you do this, you can end up with giant step, and you keep missing the minimum because you always move too much. So in this case, you have a risk of observing a divergence, and you will never find the true minimum of this function. If you plot again the evolution of the cost function as a function of the iteration number, initially you start at the same value as the one that you had in the previous case, but this case, because your learning rate is too high, you move too much and you miss the minimum, so your cost function can actually increase and diverge. So here you are likely to observe a divergence of the cost function, and you will never manage to converge and to find the true minimum of the cost function. So you will never find the optimal values for theta naught and theta 1 because you keep moving too much and you keep missing the minimum. So in practice, the learning rate should be defined as being not too small and not too large. So there is no like very robust way to say what is the optimal learning rate, because it shouldn't be too small, it shouldn't be too large, but the exact value will always depend on the specific data that you are working with. So one good way to choose a good learning rate is that you can always start with a small learning rate, because you know that it's always a safe choice. If you start by a small learning rate, then you know it's just going to take a very long time before you can find the minimum, but it's not going to diverge. So at least if you plot the cost function as a function of the number of iteration for a small alpha, then it's going to slowly decrease. So you know that in this case, if you are patient enough, you will find the minimum, but that's just a very inefficient way. You are wasting a lot of time. So a good choice of learning rate would be something that allows you to find the minimum in like a pretty few iteration. Like the more you can find the minimum quickly with a minimum number of iteration, then it means that you have chosen an optimal learning rate. So one thing that you can do is to start initially with a small value for alpha. So for example, you can start with alpha equal maybe 0, 0, 1, which is a pretty low value. And then what you can do is to plot the evolution of the cost function as a function of the number of iteration during the gradient descent. And if you see that it decreases very, very slowly, then you can try to gradually increase alpha. So you can increase by a factor 10. For example, you can say alpha now is going to be 0, 0, 1, or alpha is going to be 0, 1, etc. And you keep increasing alpha until the point that you see that your model now start to the cost function start to decrease very fast and converge. And if your so this would be for an optimal value of alpha, but if you find that now your cost function starts to diverge, then it means that your alpha is too large. So that gives you a way to find what is the best alpha. You can start with something very small and then you gradually increase by a factor 10 or maybe a factor 3, and you keep increasing until you find that your cost function decreases fast enough and does not diverge. Then it means that at this point the cost function that the learning rate that you have found is a pretty good choice, and it allows you to quickly optimize your model and to find the best value of the parameters theta naught and theta 1. So just to summarize what linear regression combined with the gradient descent algorithm does is that in practice, so you start with your training data. This is the good data, like the data that you know are true. This is your training example that you measured on a real spring, and you're trying to find a model that can interpolate those data points, a model that can represent the force that you need to apply to a spring in order to reach a given elongation. Initially, you don't know what this model is. This is what you want the machine learning algorithm to tell you. So you will make an initial guess. It can be anything. So for example, in this case, let's assume that you will choose a value of theta 1, a value of theta naught. So here, so this is the axis x, and this is the axis y. In this case, this is the elongation delta L, and in this case, this is the force. So those points are fixed. Let's assume that initially you start with a model for h of theta. You start with a model that is initially not very good, so you have to find the best values for theta naught and theta 1, but initially sometimes you don't know what is the best value for theta naught and theta 1. So let's assume that in this case you start with a model where theta naught is equal to 1.5. So you would start somewhere around here, and let's assume that for theta 1 you start with a value of theta 1 that is also a little bit higher than it should. Instead of 2, let's assume that it would be 4, for example. So it means that you would start here. That would be your initial choice for your model, which means that in this case, it means that your model, the way it would look is that rather than starting at 0, the intercept would not be 0, but it would be 1.5, so it would be a little bit too high. And your model, rather than having the right slope of 2, it would have a slope of 4, so it would increase too fast as compared to what it should. So your model in this case would look like something like this when it's increasing 2 times faster than it should. So then you would start applying the gradient descent algorithm. So let's assume that you have a pretty good learning rate. So you would start to move, for example, like this. So you would move in the direction of the lowest, the negative gradient. So you would move to this position. So now if you move to this new position, the intercept will have slightly changed. The intercept is slightly lower, but not that much. Your intercept is still too high. But the slope now is going to be much better. The slope now is going to be close to 2.5, which is much better. So now your model would look like something like this, which is still not perfect, but a little bit better. So now you would move towards a new, you would do a new step of your gradient descent. So now the negative gradient would maybe look like this, and so now you would go there. At this point, your slope would be pretty good. The value of theta 1 that you would find would be close to 2. So it means that now your model has the right slope, but the value for theta naught, the intercept, is still a little bit too high. So maybe now your model could be like something like this. Very good, but just a little bit too high. So now you will do another step of the gradient descent, and now let's assume that your gradient descent brings you here. Which means that you have found a pretty good position that is pretty good to the best possible model that you can find, with theta 1 being close to 2 and theta naught being close to 0. So at this point, then you have found a model that is very good with the right slope and the right intercept, a model that minimizes the mean square difference between the hypothesis of your model and the true data. So at this point, you could continue a few more steps of gradient descent to refine the values of theta naught and theta 1, but you are already at this point, you have learned a pretty good model that allows you to find the relationship between the input x and the input y. And so once it has converged, then what you get as an output is the program itself. So you get the model, you get the values of theta naught and theta 1. So now it makes it possible for each feature x, you can now predict what would be the predicted value of y, the predicted value of the observation that you predict based on this model is going to be based on theta naught and theta 1. So once you have this model, once you have optimized the values of theta naught and theta 1, then you can now use this model for new values of the feature x in order to make some prediction of what you think is going to be the corresponding value of y, which means that now then when you have this yellow line, you can say for each values of x, you can look at what this yellow line is predicting and find what is the corresponding value of y that your model is predicting.